Okay, let us return to our lecture number 33 now. And we now consider a model called drift diffusion model. I will only give you some hints. So far, as you remember that so far in our current model, current equation derivation, we have totally neglected the diffusion. We have considered only the drift term. But on the other hand, in the bipolar transistor case, in the derivation of current, we consider only diffusion and neglected drift. Can you tell me why we have followed this in two cases? Why we have followed these two contradictory approaches? Otherwise, they are very similar. I told you earlier, NPN, source to drain, is NPN structure. And that is, that, yeah, in one case, the injection from emitter to source, emitter to base, was caused by a base current. In the other case, the injection from source to substrate, the channel, is caused by a field effect. Apparently, that is the thing. Otherwise, there is practically not much difference between a so-called MOSFET and a bipolar transistor. Why in one case for bipolar transistor we consider diffusion theory? Of course, people consider drift afterward, which we have not done here in the class for simplicity.
Most of the bulk of the transistor doesn't have any field. Here the bulk of the transistor has a field.
Actually speaking, let me tell you, both are, frankly speaking, is for analytical simplicity only. Let me tell you, analytical simplicity is the main thing behind the whole process. You know, MOSFET theory developed from which? MOSFET theory developed from JFET theory. In a JFET, there is an N-type semiconductor and there are two ohmic contacts. Whenever you apply a VD with respect to source, potential more or less vary linearly from, because it has to, linearly from the source to the drain. So there is a field. Current flows mainly due to the field. Then you are pinching of the channel by reverse biasing the two junctions either in two sides or in one side, depending on whether it is a dual gate or a single gate JFET. And that's how the current equation was derived, where no scope of getting any diffusion kind of thing. It is a simple derivation. When the MOSFET, the current voltage in a MOSFET started with MOS capacitor. The main, in the initial phase of MOSFET theory development, it is the MOS capacitor which got all attention, because it is a very interesting thing. MOS capacitor is a very interesting part, field effect. But then when considering that you are converting the MOS capacitor into a FET by putting 2n plus n plus or p plus p plus, naturally people borrowed the idea totally from the JFET, where that people did not conceive of any diffusion, because diffusion question does not arise in JFET because there is no junction involved at the two sides, no injection, minority carrier injection. JFET is 100% majority carrier device, therefore it is very, very noise free. MOSFET is not as good as JFET from noise point of view, let me tell you. Okay? And naturally the theory, and it came. But then there are definitely some justification, because as soon as an inversion layer is formed and you apply a drain bias, there will be a current, and that current will induce some drop, potential drop, and therefore there will be a field. And we assume that the current is entirely controlled by field. But people later found that it is not a very correct picture. One should consider diffusion also. Same thing was done in the case of MOSFET, bipolar transistor also. all modern theories of bipolar transistors, particularly numerical models, they consider both drift and diffusion, which we did not consider in our class for simplicity. But in Gamelpun model will be coming later afterward, after the examination, mid-semester examination, you'll find drift is automatically incorporated. Here also, drift, so some attempts were made to incorporate drift diffusion together in modeling the current. I will give you only some hints and will tell you that how there is some more modification, some further improvement in the calculation. Therefore, when I consider the MOSFET in like this, this is my Y and this is my X, current is flowing like this. So this JD, therefore, I now write for JD, the current density moving from to the drain. Of course, this is electron current, but therefore I may show in the actual current. Normally this is VD and this is grounded. Current is actually, this is my JD. But JD, let me write now in a more, that mathematically correct form. I write JD function of X and Y. There will be some current along X and some current along. So in general, JD will be a function of X and Y and can be written as Q mu n Here also I could write gradient of, not necessarily I have to write as del Ui. It is the electric field along the Y direction. This is the drift term, and this is the diffusion term. But I could write it as grad phi also, grad potential also. And the whole thing, if you remember the quasi-Fermi level approach, this can also be written as Q dn nxy into grad of quasi-Fermi level for electrons. We called it phi n earlier. I'm calling it phi fn. So phi fn is a quasi, is the IMREF of electrons, which I derived earlier. This equation was derived earlier. I found that JD expression can be written in the same as form as the drift current expression. Only thing grad phi, the potential gradient, is replaced by Fermi potential gradient. Do you remember that? So we are straightforward entering into a model which is a two-dimensional kind of model and which considers both drift and diffusion. Now QN, this is very interesting. That is why I am giving you, because you have to understand more accurate devices afterward. This is some mathematical jugglery or manipulation, whatever you call it. So what I have done, you know that this integral of nx dx from 0 to xi is the inversion layer thickness, that is your Qn. It's very well, quite understood. Per unit area, number of electrons per unit area in the inversion layer. It can be written as, instead of it, I can express n as a function of psi, the potential, as measured. So this Ei is nothing but equal to minus Q psi. You remember that is a standard way of writing. So potential varies like this. Okay? Ei is equal to minus Q psi. Psi is the potential. So n psi d psi by d psi dx, actually it is the nx dx. But now I have changed the variable from x to psi. So I have to change from 0 to x domain to psi domain. X is equal to 0 means surface potential is psi s. And x is equal to xi is defining this point. This point in the bulk where the formidable crosses the intrinsic formula. That means this point is nothing but this line is the intrinsic layer line. The formidable coincident with the intrinsic formidable means at the band gap center. That means this is the line along which the semiconductor is intrinsic. To the left is this n type, because the formidable is going above the intrinsic formidable. To the right it is P type. I am assuming that if I integrate from this point to this point, I more or less get the number of electrons per unit area. That is why 0 to xi, it changes from Cs to phi. And naturally this point is corresponding to, you can easily find out that this is, actually I have just by mistake, this is phi f and this is also phi f. So that the total bending is twice phi f. If at a, this is of the order of phi f, not necessarily phi f. It will be twice phi f at inversion. Anyway, it should be actually not twice phi f. That is why I have written phi f. At inversion, it clamps down to twice phi f. The total bending clamps down to twice phi f. Is it clear? Then I can write it as Q. Those who are interested in mathematical kind of manipulation, they will find interest in it. However, today with the computers coming, that kind of interest is vanishing. Now actually in a device, now the current is flowing, there is a Vy. There is a Vy, induced potential due to the current flow. So I have to, that psi, whatever psi is a total psi. Now the total surface potential is a total potential, sum of that twice phi f and the drop. So what I am doing, I am subtracting that Vy from this in order to get this n psi expression. You will try to understand yourself. You see that instead of writing e to the power psi, you have standard formula of n is equal to n into e to the power psi by Vth, but that psi is now modified to psi minus Vy, because to take care of the additional drop which has been induced due to the drain current. Okay. And similarly, naturally at below, the d psi dx function, the electric field function, which you have already derived earlier, which was the same function as a function of f, that f was brought in. Instead of psi, it now becomes psi minus By. Otherwise, the functional shape remains the same. Those who are interested in this kind of analytical treatment, I will request you to refer back to those equations and see, because this is a thing which you can do yourself. And therefore, you can write for ID Is it clear? ID can be written as JDXY W, then integral dx from 0 to xi. Is it okay? Is it acceptable to all of you? W takes care of the width along the y direction, along the z direction, where along the depth, the n is varying. Therefore, I have to integrate. JD is a function of y, yet z is a function of x. So, what I am doing, I am integrating from 0 to xi, that means the inversion layer thickness. This xi is an extended. Actual inversion layer draws very quickly. I will come to that afterward. But this is the region where the electron number is more than the intrinsic number. This is a region where the electron number is more than the intrinsic carrier count. That is why I have defined it from 0 to xi. I am assuming that all the electrons in this region, and that has to flow. Xi is usually much larger than the so-called inversion layer thickness. Let me tell you, actual inversion layer thickness where the number decreases rapidly is very small, about 50 to 100 angstrom. This may not be that small. It will be of the order of 200, 300, 500 angstrom. But over this region, the electron number will be appreciably more than the intrinsic carrier concentration. That is why, and all these electrons will participate in the conduction process. So it will not be those electrons which are at the surface at the inversion layer, but the electrons which are also at the bulk up to xi point, they will also follow and conduct. So therefore, ID is simply given by JDXY W dx integral dx from 0 to xi. Now substituting the JDX, Have you seen what I have done here? You just check the JD equation. JD equation is Q dn nxy del of this. This one is now the gradient of if electron mref is now simplified to this. Only y, x component I have ignored. I am assuming that the current is entirely due to the gradient along the y direction, along the channel direction. Then this Q dn and W has to be brought because it is the okay. But then for this nxy, I have to do it for the entire inversion layer thickness. I have integrated this thing over nxy dx dy 0 to xi. Then the whole thing is taken from 0 to L and the average. That exactly takes place in the same way if you derive, if you remember the ID derivation, if you take an element of curve y and then you find the field there, compute the current, then you remember the way you have derived the ID expression, you also follow the same way, you get the same equation. And then this becomes simplified to W by L. So I am giving you just the hints. I told you I am not giving all the steps. So I get ID expression as a double integral over potential so far as V is concerned 0 to Vd, that means from 0 to L means 0 to V, and over psi, and that is from phi f to psi s or psi s to phi surface to the point xi. Okay, I have written it in this fashion because psi s is more than phi f, just inverted. Sign has been taken into consideration. It's a double integral where you know that ultimately after this integration what you get? I get it as a function of Vd and psi s and phi f. Because these are this equation, these integrals, the definite integrals, the limits are Vd 0 and psi s phi f. So after doing this integration, I get it as a function of Vd, psi s and phi f. And then you know that Vg dash is equal to Vg minus Vfb is equal to Qs divided by Ci plus psi s, and that is equal to twice epsilon s Kt, which you derived earlier, Ci Q Ld into f of psi s. So what you can do, for each value of Vg dash, you can calculate psi s. Which one is easier? Calculating psi s from the value of Vg dash or calculating Vg dash from the given value of psi s? Which one is easier? Second one is easier. So you can do the second one, and always you can use that curve for translation. Instead of numerically, and otherwise you have to, it's a transcendental equation. So if I want to calculate the value of psi s for a given value of Vg dash, you have to treat it as a transcendental equation, and solution is not that. You have to do some numerical step. Otherwise, you simply have to generate a plot, and to interpolation, you can always find out the value of psi s for any value of Vg dash very easily, so far as computational procedure is concerned. Then for a given Vg dash, you know what is the psi s. Then for that psi s and that phi Vd and phi f is known, you can compute ID. So this equation is a more comprehensive model. Only thing is, this has to be done numerically or semi-numerically. This integration has to be done numerically or semi-integration. Numeric integration is much more easier than using a finite difference technique or finite element technique, where convergence is a great problem. But on the other hand, integration by numerical technique is rather simple and very accurate you can achieve. So using all these things, people are able to plot the ID versus VD characteristics. Which is considered to be more accurate. Advantage of this technique is you don't have to stop at a certain point. You remember earlier, in our earlier derivation, I drew a boundary. Okay, and these points were defined as VD set, ID set points. A particular value, I call it VD set, and particular value is called ID set. all those equations which were derived earlier, they are valid only up to that Vd side. Beyond that, I assumed it constant. And that assumption was based on that velocity saturation is that effect. So if you use this model, you can get the full curve. And people have found that for at least long channel devices, these curves agree very well with experimental data, much better than the other one. So if some of you are interested, you can take it as a challenge. You take a device, write a simple computer, that small program to be used to solve this ID equation numerically for given values of Vg and Vd. For any values of Vd and Vg, and of course for given structure, you can compute ID as a function of Vd for different values of Vg dash. Okay? This becomes more challenging than the stereotype class things, whatever we have presented so far. So some of you, if you are interested much, you can take it up as a home task if you feel so, or just as a small project. Okay? Should I give it? After the examination you attempt it, you assume Na is equal to 10 to the power 17, W is equal to 10 micron, L is equal to 1 micron, thickness of the dielectric is 350 angstrom. I am not going to the very small devices, and say you dielectric constant is 4, that means silicon dioxide insulator. Which else you need? VFB value, you calculate, you consider N plus poly gate NMOS with these features. You know everything now. QF you consider to be 10 to the power 10 Q I think I have given you everything. Epsilon S for silicon is 12, epsilon silicon dioxide is 4 multiplied by epsilon naught. All these values are given. You generate this curve. It's a very interesting thing. If you can practice this, you will learn much more than whatever you have studied in the class. Now let us really enter into another very important aspect of MOSFET called subthreshold conduction. For Vg, that means over this region, what will happen? N at the surface, that means N0, will be more than Ni. Am I correct? N0 will be more than Ni. Therefore, we can say yes, this is under this condition. There will be some appreciable number of electrons which will cause some very minor current flow, not a very major current flow, a small current flow, a small current. And that is what is known as subthreshold conduction. So I see that when Vg is even less than Vt, but as long as it is more than Vi, that means the corresponding surface potential is more than phi f, but less than twice phi f, then also a small current will flow. And this current is called subthreshold current. In the normal range, the currents may be in the order of milliamperes, but in the subthreshold range, the currents come of the order of microamperes, okay, or nanoamperes. But when you consider today's VLSI, where so many components are packed, power dissipation is a very important parameter. So you are sometimes tempted to use these devices even near threshold or subthreshold region. It's very important for you. And then I must understand how the conduction physically takes place in the subthreshold region. In the subthreshold region, you see that EY can be considered to be 0. Because practically there are negligible number of electrons, the current flow is so small that the potential drop in the channel can be neglected. And if there is no potential drop, the potential gradient will be 0. So electric field in the channel at any Y can be neglected in the subthreshold region, which is not true for overthreshold. This is true for subthreshold region. Under this condition, therefore, what is going to, how the current will flow? Because in this case also, the barrier, as you have applied a surface potential, a gate voltage, which makes some psi s, what will be the potential barrier at the source end? VBI minus psi s. That psi s is not twice phi f, but between phi f and twice phi f. The barrier will be lowered at the source end. Electrons will be injected, and that electrons will flow from the source to drain. And what should be the, because Ui is equal to 0, what will be the mechanism of current flow? Only mechanism left is diffusion. Because Ui is equal to 0 and electrons are getting injected from source into the substrate channel, the only mechanism by which the current will flow from the source to drain is diffusion. So it will be very similar to our bipolar model. In that case, therefore, ID can be represented as QA. A is the area of cross section of the channel, dN into dN dx. Let me write dN dy, isn't it? Not dN dx. Okay? And that can be written again simplistically, as because I am not interested in deriving a very comprehensive equation, but just to look at it and see how it should happen, a qualitative aspect, I simplify it as the dN dy, I linearize it and assume it to be the slope between the 2 endpoints, assuming a linear distribution, where n0 at the source end is np0 e to the power psi s by Vth, and nl is equal to np0 e to the power psi s minus Vd. Assuming a small Vd applied. ठीक है? Then here one thing you assume that you see that I have to estimate the what is the, if you know that here I have written A, area of cross section of the channel, and in that case area is equal to W multiplied by Xi. No? Xi, the way we computed earlier, instead of doing so, I do the following. I assume that the inversion layer, this is the inversion layer, okay? This is the inversion layer. I assume that from the surface to this point, if this is psi s, then the fall from the surface is a thermal voltage. Then this is my inversion layer thickness. I call it xi. Earlier, you remember, inversion layer was defined the point at which, for earlier derivation, that is more important for the total current flow. But here, because the number of electrons will be very few, and they will be distributed because of the, that in metal also the electrons are all located at the surface because of the repulsions. The electrons will be mostly located at the surface, and because your potential is very small, psi s is now less than twice phi f, they are located practically at a very shallow region, and we assume that it is a region at which the potential falls by VTH. VTH is a thermal voltage. Then this effective thickness of the channel can be written as VTH divided by the surface field epsilon s is a field at the surface, normal component x. Because we are considering both y and x, therefore field at the normal component of field of the surface. That is xi. This is a simplistic derivation, let me tell you. And epsilon s, on the other hand, is given by minus qd by small epsilon s, and that is given by from Poisson's equation. I know that the Gauss's theorem, we get this one. Substituting that epsilon s value here, this value here, then what is my A? A is equal to W multiplied by xi, and that means W multiplied by VTH by epsilon is x, where epsilon x is given by this. Substituting them in this equation for current, where N0, NL are represented by these two, we ultimately simplify this current equation in this form. After mathematical manipulations, rearranging terms, etc., you get ultimately ID in this form. And from here you know that ID is, in this case, is proportional to 1 minus, so far as VD dependence is concerned, it is like this. Whereas so far as psi s dependence is concerned, that exponential term is more important. and which is equivalent to roughly e to the power Vg dash. Not exactly. We can say that if ID varies exponentially with psi s, we can say that it will also roughly vary exponentially with the applied gate bias. Not exactly, but we can easily find, you know the relationship between Vg dash and psi s. For each Vg dash, you can compute what is the psi s, therefore you can compute ID. And it is possible from this equation, which is rather simple model. Let me tell you, it's not a very, very accurate model. At least some idea of ID, how it depends on Vg and Vd in a subthreshold region can be more or less calculated. And if I do so, the kind of plot it generates looks like this. Usually this is a log of ID, logarithmic curve. Starts from say picoampere, maybe a curve like this, 10 to the power minus 10, 10 to the power minus 8, 6 ampere. The curve looks something like this. This may be for Vd is equal to, and voltage may be some voltage. I am not giving some scale. It is maybe 1, 2, 3, 4, 5. A very typical case. You can have your actual computation, but this is a very typical thing I am telling you. There's some idea. This may be Vd is equal to for 0.1 volt, whereas the other curve is Vd is equal to maybe even 10 volt. And for this, I have assumed Vbs is equal to 0. You see that in the logarithmic scale semi-log, the behavior is almost a straight line behavior, linear rise in the semi-log, that means the exponential increase of ID with Vg for small values of bias, gate bias, but as gradually it tends to saturate, and for different values of Vd the curve do not vary much simply because of this term. Okay? This is under the assumption that no substrate bias has been applied. If you repeat the same experiment with a substrate bias applied, you will find that the curve simply shifts, otherwise there is no basic change. So this is Vd is equal to 0.1 volt. This is Vd is equal to say 10 volt. But for this whole thing, Vbs may be some 4 volt, maybe anywhere. And one thing you note as a result, this point is an interesting thing, you know, that this way defining threshold voltage is called dynamic definition of threshold voltage. It is the voltage, gate voltage at which the current crosses a certain minimum value, maybe a microampere or 10 minus 7. Say old devices, we used to define it as 1 microampere level. In modern devices, we define it as 10 minus 7 or 10 minus 8 ampere level. The voltage at which the current crosses, that is called threshold voltage. Whereas the other definition of threshold voltage, analytically, what was the threshold voltage? The voltage at which phi s is equal to twice phi f. Where the voltage, in this case, it is a voltage. Which one is more practical? This one. When you make a device, you can easily find out these characteristics, and you can find out these Vt values so easily. Now, can you tell me that which one is desirable? The slope, you have shown that the slope is practically a constant so far as in Smemy log graph is concerned, because of the dominance of this e to the power psi by Vth term. As a result, this term dominates. Okay? So it is this slope. Which one is desirable? A stronger slope or the narrower slope? That slope. A small slope or a large slope? Which one is desirable? Larger slope. Because in that case, it will suddenly be cut off properly. Therefore, when we define a MOSFET, we should define another very important parameter, which is called subthreshold slope. It's a very, very important parameter, the slope of this curve. What is that subthreshold slope? Here you see that